Think about the process of sending a letter to a friend. If we didn't have the organized services and standardized addresses of a post office, moving a single envelope across the country would be absolute chaos. In the late 1970s, the digital landscape faced this exact problem. Early computer networks were expanding rapidly, but there were no universal rules for how they should exchange information. Different manufacturers built their hardware and software using closed proprietary systems. A machine built by one company simply couldn't decipher signals sent by another. They were isolated islands of data. To bridge this gap, the International Standards Organization, a multinational body established in 1947 to solve global communication barriers, stepped in. By the late 70s, they introduced a framework designed to force worldwide agreement on digital communication, the Open Systems Interconnection, or OSI Model. This is the architectural blueprint for networking. By dividing the complex process of communication into 7 specialized layers, the OSI model establishes the framework for global computer compatibility. Let's start at the very bottom of this structure, Layer 1, the physical layer, where data exists at its absolute smallest scale. This diagram illustrates the physical layer's sole responsibility, transmitting individual raw bits. It pushes sequences of ones and zeros directly across a physical transmission medium, like a copper wire or a fiber optic cable. But raw bits streaming over a wire are totally disorganized. To give them structure, the system relies on Layer 2, the data link layer. Here, we see how the data link layer takes those loose bits and organizes them into manageable packages called frames. It attaches specific routing and error checking information, an H2 header and a T2 trailer, around the core data payload. This layer focuses entirely on what is called hop-to-hop delivery. Looking at the bottom left of this network map, you'll see the data link layer only oversees the short, immediate jump from one physical node to its very next neighbor on the path. Moving a frame to the nearest router is a crucial first step. However, that local router lacks the overarching awareness required to navigate the massive global network and find the final destination. That requires Layer 3, the network layer, which handles the complex geometry of global routing. As this schematic outlines, the network layer takes the data it receives and wraps it in a new package called a packet. This adds an H3 header containing the precise logical addresses needed for the entire journey. This highlights the network layer's defining job, source to destination delivery. It maps the overarching route from the initial source to the final target device. Notice the contrast. The data link layer manages small, individual pink hops, while the network layer guides the continuous end-to-end trip. This 3-tier foundation, translating raw bits, structuring them into local frames, and calculating global routes, is how the system moves data across the gaps between different physical networks. Once the data reaches its global destination, it still needs to be prepared for the actual human user. This breakdown shows the roles of the top 4 layers. The transport, session, presentation, and application layers take over to manage reliable message delivery, establish distinct software sessions, handle data encryption, and finally, allow your specific application to access the network resources. All 7 of these layers function through a strict process called encapsulation. When you hit send on a message, the data starts at the top of your computer's stack. As it drops down through each layer, it gathers a new functional header, wrapping the data repeatedly before it hits the physical wire. When it arrives, the receiving computer performs decapsulation. The packet travels up the stack, and each layer sequentially strips away its corresponding header until the final message is exposed to the user. Because of this mirror image design, we achieve peer-to-peer communication. The network layer on the sending computer logically talks directly to the network layer on the receiving computer, entirely independent of the layers above and below them. The OSI model provides the framework for this interaction. These 7 specialized layers act in unison to maintain a single set of rules for worldwide communication.
Thanks for watching this video. If you want the notes, just go to the description and tap the Google Drive folder link. But make sure you're subscribed before accessing them.